So I'll conclude it more quickly unless you have questions. This is more interesting topic, the one I'm going to see in the next 25, 30 slides, but I'll go faster, you will understand. So our mission is to do what? Adoption of polymer composites. We did all these in the field, please note. We are not exaggerating any bit of it. There's a lot more to be done, mind you. Highways, bridges, buildings, pipelines.
You mentioned transmission towers.
Transmission towers. That's right. That is utilities and energy.
Utilities.
Right.
Utilities.
Right. It comes under. I'll tell you a story. I don't know whether I have a slide here or not. The pipes that we built with composites, we can replace, and we are replacing your what we call lattice structures for transmission towers, like 120 feet,
Right.
with a single 20 to 24 inch diameter pole. There's a lot. If you go to my other presentation on the fire of the utility pole, I gave that to, where is this guy? Oh, here. Yeah, I gave that to him. So you can see all the fire tests we did, all the thermomechanical tests we did, so you will see all that. But that we
because you had last year,
right,
2024.
right. So this is a hydraulic structure. So I built the first structure in 2013. You know, these end users are not sure how well it's going to work. They waited 10 years. 2024, they're happy, satisfied with it, and they gave $60 million contract to a private company that produces these wicket gates. We call them wicket gates. I'm sure there are many wicket gates in India, more so than in US. A wicket gate is limited hydraulic depth, like 6 feet, 8 feet, and it goes up and down. Anyway, I don't know, some of you claim hydraulics people, so you know better. That is the gate. This is made of a composite. And we made it at roughly half the cost of a wooden gate.
Thickness, what's the thickness?
Those are about 10 inches. 10 inches. That's about 250 millimeters. So,
and length, maximum length?
we built up to 20 feet.
30 feet.
That's what.
So, compared with the vertical lift gates,
Right. We went up to 20 feet.
20 feet.
So anyway, this is the vacuum processor, Mr. Chan. You see at the bottom, look, there's a huge amount of science behind it. Not little. What is the vacuum process? What is the science behind it? I'll give you very quickly 2-3 lines and move on. What is the port spacing and the size when you vacuum it? What is the speed at which you are going to vacuum it? And if you are going to vacuum at a atmospheric pressure, you cannot exceed 14.6 or 7 psi. But how can you do the vacuum process at a higher pressures? You know, those are and what temperatures? There's a lot of fantastic opportunities for the students to kind of research into them. And anyway, again, what's our goal? Our goal is to insert as much shell fabric, glass fabric, and that particular cross section has a good bit amount of core material which is not a composite. My student will come, he will show you, he's here, he's working, he has his own company in Hyderabad. He is actually building a core material, what is known as a syntactic glass core. So that gives you fairly higher strength, or you can use low grade core material, but that is mostly a composite shell and mostly 80% is low grade core material.
This has been put to test already?
Oh, they're producing, you can see. They're,
I know, but has it been put in practice?
yeah. You may, no, he did. Oh, that's why I said, they put it in practice 2013. They weren't sure it'll work or not, so they waited, monitoring it.
It's a long time.
That's what I said, our gestation period is 30 years.
13 years is long time. Anyway, research is what it is.
Yeah. That's what they're happy about it. Again, I guaranteed them 100 years service life. So anyway, going back.
The problem, I'm sorry for the interruption. This is typically what happens in hydraulic structures is they get worn out in less than 10 years, 5 years. The gates get jammed up, especially in flood situations, you had it.
So that is the fabric configuration before it is infused. That is, this is laid there, this is the infusion process, and that is the final product. I mean, I summarized 5 years of work in 5 seconds. So that these are complex issues. That's all my point. So this is the sandwich manufacturing. So that is, you see the sandwich there? That is the foam core. That is polyurethane. In this particular case, that's polyurethane. And you see the shell, which is the composite. See how thin it is? So these composites are lightweight and very strong. Okay. Why did I keep saying composites are low in stiffness? I already told you, right? They are 1/4, 1/5, 1/6 of steel. All right. We do not design based on modulus. We design based on modulus times the moment of inertia, EI. The flexural rigidity is the key component. There's a lot of misperception that because the modulus is low, you need to have higher value. No, it is the EI. Why am I saying that at this juncture? Because what's your guys, Gopal or somebody? What's the name of the prof who left here? Raj Gopal. So he was wanting to do a lot of work in the. So look at this. Why did I separate the two? It is the AD square effect. So by separating the two, my AD square is much higher, even though my modulus is low. So the E times I compensates to the level I want. However, one needs to be cognizant of the failure modes before you can get into these kinds of optimized designs. So, did you get the point? You may not be able to do it, but did you appreciate the message I gave you? EI is what drives the stiffness. E is low, therefore I need to bump up I. That's what we did. I'm very proud of the all composite bridge I built in 1999. This is a single span, 175 feet long, and this is also a jointless bridge. And the deck system that you're seeing is all composite. That is what you see there under construction. This is the finished product.
This is right in Mogaton?
No, this is in closed, Wheeling, West Virginia. Yeah.
Wheeling is a little away.
That's right, about 80 miles.
Yeah, I remember.
But it's in downtown, next to the industrial park.
No.
You remember I just said a minute ago, the stiffness is a product of E and I. That essentially, I don't want to get into all the details, but that essentially speaks for it.
Sorry, one question here. Why do you have to have so many different geometrical figures? What explains that?
First of all, I got several patents on this. You know how I got the patent? I visualize this. If you look at that is the structure.
Yes.
That is a beehive structure.
It looks like that.
It is. That's where I got
You got the idea.
idea.
It makes sense.
So there's a lot of things we can learn from
Nature. Absolutely.
That's what it is.
And the second shape?
You were asking me why so many? What did I say? Composites are weak. You know why I did that? Because I was reducing. Let me first talk about failure mode. There are, for a good design, how do you optimize a cross section that would result in a failure at the same time of all the 5 or 6 different failure modes? That is, okay, number one. Now I'll describe. That's a broad statement. That's a scientific statement. I don't speak extra word if it is not needed. Therefore, make note of all the words. Okay, now, first of all, we had to maintain typically 8-inch thick deck, because that's a conventional concrete deck on a highway system. Some may be 10 inches, some may be 7 inches, but typically it is about 8-9 inches. Some are not exactly, but okay. So that's one thing. You understand what okay, 8-9 inches. From there to there, it is about 8-9 inches. That's my constraint.
So it's depends upon the application where it's going to be used in the construction. Places of the construction is required for that design criteria. I think so. Is it?
The construction can be made modular, and that's what we did. And you can replace a concrete deck. And oh, I didn't mention that. I built that is 58 feet wide, 59 feet wide, and I told you 185 feet. So this is over 12,000 square feet. The deck, I built that in 4 days. Okay, now let me get to your point. Why I'm saying that is we modularize these decks and be able to place them in a manner that minimizes the construction time, minimizes the accidents at the construction site, because we have max accidents at the sites. And it fits into whatever the standardized approaches they do, because I have to conform to them. Otherwise, they will not put a deck on a main highway.
Practical limitations.
Yeah, there are other limitations to it. Because if I have a bumping up or bumping down, they don't like that. So those are a variety of constraints. So at any rate, trying to answer your question, the buckling, I don't know how many of you remember the Euler buckling issues, pi square EI or L square type issues. The buckling of that mini column, I had to constrain that by restraining at a certain distance. That's what I did. That's one of the many other issues. These are not that simple. I'm just...
That's not simple.
No, I meant it. What I speak is far simpler than what goes
Everything
in.
has a meaning here.
Yeah, that's the primary thing. So I'm kind of proud about this one. This is only 4-inch deck, but able to be placed on an interstate highway. We call it 18-wheeler. That takes 80,000 pounds. So that deck at 4 foot, 5 foot spacing took 80,000 pounds. And here are the foam or wood decks. This is the one I told you, this particular deck went into destroyer class of ships. There's your FRP rebar. I am very proud about it. First bridge in the world we built and still standing. No. I mean, I had a lot of resistance on this. I said, I'll stick my neck out, stick my license out, and we built it.
96?
96. 95, we finished it, opened in 96. So you can see that is the McKinleyville Bridge. It's a 3-span continuous bridge, no joints. Okay. This is a highway we built in West Virginia, Route 9, close to Washington, D.C., reinforced with FRP, CRCP, continuously reinforced concrete pavement. So this is, I built half mile with the FRP, half mile with steel. We made the comparisons. Primarily, what do you compare? Crack width. Primarily in a highway system, not a bridge, you see. So anyway, that's an application. And
it's only the deck. I think the girders are probably.
No. This is a highway.
Okay.
I'm talking about this is a highway.
Okay, it's a highway. Okay.
Right. That is a bridge.
Okay.
I built all composite, including the decks, but I'm not showing that here. But yes, you're right. The bridge, the McKinleyville Bridge I built, is a jointless bridge with 180 feet long. That is only the deck with concrete. The girders are steel.
Okay. Based on steel.
That one. But there are other bridges.
You can see them.
So again, you see that is the Band-Aid. You know what a Band-Aid is? You use the word Band. Okay. That's a Band-Aid for a interstate bridge. That column is that one. That column is 42 feet. It split open because the bridge was in a slope and it was moving, and they said it'll cost about $4 million. I said, give me a chance to wrap it. Again, there is a lot of science behind it. I won't get into it. Maybe if you become a student of Dr. Prakash, he'll teach you how to do that. But we wrapped it in 2015, and we did it. Replacement is a $4 million. We did it for somewhere around $300,000, 0.3 million, somewhere in there. I don't remember, and it's doing extremely well. This is the Army Corps Bridge. This is a pre-stressed concrete bridge, and the strands were breaking. As you can see, when we dug up, we saw broken strands and whatever, various intermediate steps are there. That's the message I want to go from here to here. There are very many intermediate steps. I will leave that in my textbook on concrete. You will see those steps. This is done in 2011.
So is this of carbon or glass? Foam it is carbon.
This particular one is carbon. All right. It could, the pier is also carbon, but we did many other bridges with glass. Now wait, why did I use carbon here? Because I lost some stiffness already. So I want to bump up the stiffness. Therefore, I used a high grade, high modulus carbon. If it is only for aesthetic purpose, if it is only to prevent further degradation, I could have used glass. And I did use glass, but not on this application. So it can be both, either or.
So there is
Go ahead.
so any structural health monitoring is in
Oh, yes, we do that continuously. And actually, I haven't started my project. I'm going to start my structural monitoring. They just gave me the money. It won't start till September. That's where I want you to come and train yourself at our place. So we will see how that goes. This is the World Trade Center. Remember the World Trade Center where it was near that? This is a pedestrian bridge. I'm right now testing a 100-foot long pedestrian bridge. I tested a 70-foot long pedestrian bridge in my lab. I have a big lab. I have about 15,000 square feet of open lab. So now I'm testing a 100-foot one outside. So
A new one.
this is a new one. Yeah. I rehabilitated, that's wrapping as you can see. That was a bridge, there's several bridges, built in 1908. I rehabilitated. You see how badly timber was eaten away? So this is the end product of that. All I want you to understand from this, yes, you can rehab a system, but the matter is you must know what the heck you're doing. This is the sheet piles. So I'm just showing you different kinds of applications, nothing more than that. And this is the pipe.
Your lab, right?
Right. That's my lab. But no.
Yeah,
This is the 120-foot high utility pole for high tension wires. You know what? 4 times cheaper than your standard lattice structures. They told me, I'm well tuned. I'm only talking of my successes. I had a lot of failures as well. Let me tell you that much. I don't want to. Okay, one of the major failures is, as I told you, I look at things from the mathematics point of view. They said, no, you come down to our level. I was giving a major presentation at American Society Astro people. You know what? This is in 1977. I'm not ashamed to tell you this. You know, that is where my math thing comes into unfortunate hurdle. It's fortunate in a sense, but I look at it differently. But the unfortunate part is, I was making this major presentation. All these 50 chief engineers from the 50 states were there. They gave me an hour. After 10 minutes, I was so humiliated, but I learned a lot. After 10 minutes, they said, stop. I said, why? We don't understand a bit of what you're talking about. That's what they said. I thought, gee whiz. What a fool I made myself, you know. After all, if you don't learn how to communicate, I'm not trying to be here to impress you, right? I'm here to teach you. So if I don't know how to communicate at your level, I haven't done the job. So anyway, this is the application, another application. And this is the pipe. We test up to about 50, 60 feet in single span. This is the bridge I'm talking about in my lab, 70 feet long bridge. Then we built it at Bermuda, as you can see.
It's now in the Bermuda Triangle, I suppose.
That's a famous Bermuda Triangle.
Bermuda Triangle.
Yeah. So you can see the all FRP bridge.
Oh, the low gate.
These are all gates, and you were asking me, where did they implement? Right there.
This is a good example.
Right there, they implemented it at Peoria, Illinois, a famous Mississippi River, very turbulent river. That's where they built that.
When was this done?
No.
For visit?
I didn't do, I must quickly say that. This is mine. I did not do this. This is done in Netherlands.
Oh,
They-
this is Netherlands, is it? I see. Okay, that's yours.
Right, right. So,
Piank, this is from Piank.
Piank, that is the infra core.
Right?
Yeah.
Piank.
Oh, you do? Yeah. I chair the composites division of Piank.
Nice to know about Piank. Right, hearing of a long time.
Yeah, yeah. So, we are now building these now. Yeah. So, I knew very little about hydraulics structures, you know. So this general listened to a story in Netherlands about the composites. He came back to US, you know how these generals talk. He growled at a meeting like this, how the heck America is not doing anything. One of my students happened to be there and he said, sir, I know who can do the job. So that's how I started my work in the hydraulics area in 2006. Yeah, as a very coincidental type thing, so we did that. Now we are building these structures now. So we call them stop logs. That is where we can use the core material. So we can have different grades of core material, and then we have a shell material, and then how we put it all together to maximize the strength and the stiffness. That's a hydraulic structure. And again, all we do has no meaning if we cannot produce it in a durable manner and in an economical manner. So those are the two ultimate goals for us. That's a close-up.
Was also in Netherlands.
That's right. The service life, yeah, I work with them very closely as a chairman of a composites division. This is mine. The steel is corroding so badly, so we use the composite. And now they want to build many more.
Was Ohio River, is it?
Yeah, it's Ohio River. Again, we talk of rehabilitation of structures. The piles are getting corroded, and you can see we brought the capacity. We kept talking about 3 sigma and whatever, you know what? The civil structures factor of safety, you know how much it is? 10. So after I built it, I said we monitor it. Typical failures from the yield point of view of steel is around 1600 micro strains. Whereas when we tested that with a full 80 kip means whatever that is, 600 kilonewtons truck. You know what? We didn't even get 150 microstrains. What did I tell you? 1600 is the yield value. I only got 1/10 of it. So the guy was wondering, is my equipment working right? Is this, that, whatever. They're paying for it, right? So I said, look, that's what happened. That's what the civil structures people do. The aerospace structures, the factor of safety? 1.5. So that gives you an idea how stringent they are. It is their mechanical systems sometimes that fail. More often than not, it's a human error, not really. Yeah. So that is the hydraulic structure I built. He was asking me, did I field test it? It was field tested in 2015. This is my lab. That's where we did all the fatigue testing, all the flotational testing, and what have you. That is the utility pole.
That's what we were talking about.
That's right.
Oh my God, look at that.
Fire is a big science. I won't go into all the detail. All I want to say is the following. That is, composites degrade, I already told you, with temperature. A quarter inch, roughly speaking, a quarter inch thick composite has about 40 layers of a 24-ounce fabric. 40, roughly, plus or minus. We found that it takes about 30 to 40 seconds for each layer to degrade at a rate of about 1000 degrees Celsius. So translation of that is 40-45 layers. It takes about 20-25 minutes. All right. That said, two important things I want to add to that. If I apply a coating, which is, we normally call it
Fire retardant.
as intumescent coating. If I apply the intumescent coating, I can increase the fire resistance from the time point of view. The other improvement from a fire time point of view is we have a fire shield. We put a shield around it and lock it. So the reason I'm saying is, recently, meaning in the last 5 to 10 years, we have a lot of issues with wildfires in California. So we are using this now. Of course, resistance to change is there, but at least they identified where they have these very, very serious fire problems to use this.
How recent was this?
We have applied a couple of 3 years ago. EPRI, Electric Power Research Institute, gave me a grant to try to.
Recent is in Los Angeles?
That's right.
Yeah, that's
These are about 2, 3, 4 years, but they're happening every year now.
That's happening every year.
So we want to protect the main lines, the trunk lines, if not the feeder lines. So we use now an intumescent
It's a
coating.
very big application.
It's a big application. Yeah.
So the intumescent paint coat, typically because these are power is an essential, facility. Even let's say after you extinguish the fire, then still the poles have to be operational and so on. What is the level of coating? One. The second is typically, we use this as I said, shielding, some kind of a shielding. Typically, we use this calcium silicate-based boards for fire retardant. So both of them, how much the cost goes up compared to the normal your concrete kind of coats?
Intumescent coatings are not only improving in terms of the quality, but also becoming cheaper. That said, I'll give you the numbers. Including the labor cost, it is less than $1 a square foot, including the labor cost. Again, if you have large quantities of coating at a given site, it will be cheaper. If it is just a very small quantity, it will be expensive. So economics is a matter of a volume issue. So you can see that is the California wildfires, we call it. And there are stringent issues they gave me. They said, I must test it at 1120 degrees Celsius
1120.
at 3 minutes.
Oh gosh.
And then they said, how much is the degradation in the material strength after the 3-minute exposure? So a lot of ASTM type issues. I didn't do this, somebody else in France. So composites can be used. Somebody asked me in this country, the solar panels, using the composite, because they're lighter weight, they're non-corrosive and all that, and at the same time you can accommodate solar cells, So anyway, there is the example. The air mobility. Somebody said that my alma mater, IIT Madras, has done a drone that's going from Chennai port to Calcutta.
They are on trial basis.
Trial basis, but it is there. See, look. I came from originally from India, then moved there. But our innovations are getting a little slower due to one reason or the other. I won't get there. But really, sky is the limit for India to avail the opportunities for these innovations. Anyway, the concluding remarks are there. So we're talking about 15 to 25, 30% is the conventional, is the cost compared to the conventional replacement. That's the bottom line. And we guarantee you 100-year service life. That's another thing. Those are the two things. But what comes with it? You better know what the hell you're doing. That is don't just get into engineering without knowing the fundamentals. The critical thinking is extraordinarily important. Not just copying from one drawing to the other. Nothing wrong in copying. When you're doing that, you must know how to translate one to the other. What are the issues? I think that concludes my, these are several references. That doesn't matter. You will find them in your handout that
let's give him a big hand. Excellent lecture. Very well educated. I hope you like this.
Sure. So, Professor Gagano, I think any questions from the participants?
no question is a stupid question. Any question is important.
The more questions you ask, the more interested you are recording.
Yeah.
I'll come to you. Chandan, go ahead first and I'll come.
So regarding the
But a little louder.
so regarding the incandescent range of PCLC, so just wanted to know about the compatibility of this with the FRP. So many different based material, which material is really compatible.
That's a very good question. I have not tested for the compatibility other than the fact that I have installed it. So, when I say I did not test, I meant in terms of ASTM-based type of testing. But I did test for high temperatures and what have you in my lab, like 1120 degrees Celsius. I did that. But I did not test from the compatibility point of view. They are surviving for 5, 6, 7 years. If you ask me, do I guarantee 100 years? I don't, because I haven't done the work. You follow me? I think I made a statement, if you remember. What did I say? I said, we follow certain protocols, test these material, and then we apply certain theories to project the 100-year service life, right? One guy asked me, you keep saying 100-year service life, you will be long gone. What's the guarantee? So we showed how we arrive at those numbers. So from that standpoint, I haven't done but from a crude standpoint of, did it work? Is it working? Yes, it is working so far. Even if I had to repaint it with an intumescent coating after 10 years or 15 years, it's still well worth it. Because the rehab part from a fire resistance point of view is much lower.
So, but that's, just to add to Professor Yohannes, anyway, even in steel structures, right? For this one building, you see the black color, these are all intumescent coats. Maybe some locations you don't appeal on, but then you have to go back and repaint it, right?
That's right.
So that's one. Second thing is all material, they take concrete or steel, under fire even they degrade. Maybe they may degrade slightly less slowly than, or more slowly than FRP, but still they degrade, right? So after that you can go back and replace that one few damaged elements.
Right. So I don't have a scientific argument, that's all I'm trying to say. But we have developed some recent coatings that have, like I said a minute ago, coming down in terms of the cost. Yeah, you have another thing?
Just an extension of it. So we have a epoxy-based material, intumescent paint, and water-based intumescent paint, and also acrylic-based. So which one is very much compatible with our paint?
We prefer the water-based paints. The idea, what is an intumescent coating? Let's start with that. Again, you need to go to the fundamentals, right? So when it warms up, it releases the moisture. And it is that release of the molecules of moisture protects the... So if you have a decent quality water-based, those are ideal.
Sir, I have a question. In normal these carbon fibers and carbon wraps, people are always asking for the tensile strength which it can offer, the individual carbon fiber. So in India, we are struggling a lot to find out laboratory where the individual tensile strength can be determined for the carbon fiber. So any suggestions on that?
I don't know about India. We do that routinely. A single fiber, Instron machines are there that would break a single fiber. So in other words, I have machines going up to a maximum of 1 kilonewton to million kilonewtons. So it depends on the kind of machine you want to employ, but yes, individual fibers. Not only that, we have certain kinds of instrumentation that would determine the modulus of it.
And how do we compare these glass fiber composites, the rebars, the tensile strength of the rebars as compared to the carbon fiber and carbon wraps?
Okay, I haven't come to...
Add to you, I think in this part of the demonstration, we will also show you, we have a facility, we don't test individual fiber, but we test group of fibers to get an idea. That's what the ASTM standard says. We will show you how to do that, prepare the sample and test it. We also have an install machine, as Professor Gangarao said. We'll show you and comparative thing also. Yeah, please go ahead.
To answer your question, as you know, I haven't come to that yet, but I will, of course. First of all, let me say this. The strength or the stress to failure of a material in a composite is a function of the bar diameter. Let me start with that. Let me explain that. What does that mean? If I have a 1-inch diameter bar, I get, say, 100 units. Whatever that, I can spell out the number, 6570 KSI. That is the strength of a 1-inch diameter bar, which translates to about 500 MPa. But if I go to a 1/4-inch diameter bar, I'll get 100, double the strength, let's call it. Let's not get into the relative. Why? Because you have what is known as a shear lag problem. In other words, if you want to become a millionaire, find a way to improve the in-plane shear strength by having discovered a proper resin system. I got a call one day. I did a lot of work with the pipes. I may talk, may not talk. But one day I got a call from Saudi Arabia asking me to do it. I said, look, I can only do the pipe. I don't know how to do the joint, because the joint is a function of the in-plane shear. That is the same problem with this. The in-plane shear. So, when I talk about a shear lag, what does that mean? What is a shear lag? It is when I grip the bar in the Instron machine or MTS machine, there are two chucks, right? And you grip it. And then you're going to pull it. The load is transferred from the outer surface to the core. Even in steel, we have shear lag, but it's extremely small. You don't even see it. You don't even know. Whereas in a composite, because the shear strength, I kept telling you over and over, the shear strengths of the resins are lower and lower. Therefore, the outer fibers resist a lot more load than the core fibers. So I plotted the thing by using the acoustic emission technique. What fibers failed first as I'm pulling it, vis-a-vis what are having a delayed failure. The outer fibers are failing much earlier. What does that mean? Even though my average value is 100 units, my outer fiber values are 150 or 200 units, the core values are 30 units or something. You see, understand now? That is what is called a shear lag problem. So, because of that, we will never be able to, if you are going to restrict yourself with quarter inch, eighth inch, yes, you get 150 to 200 KSI. Again, I had to convert that 1000 MPa type thing. Whereas you go to higher diameters, you don't get that strength. Okay, that is from the glass. With respect to carbon, we have very high strength individual fibers. We can restrict the equivalency of load transfer by about quarter inch to half inch. Therefore, you do have a shear lag problem even there, but not as severe as it is in a glass fiber composite. Did I answer your question, or did I convoluted it? This bar, people like to think that they can mimic it by wrapping at certain pitch. You know what? It will improve some of the strength, all right. We have a lot of different failure modes. It fails sooner than later with the wrap, with this, whatever you call it, looping, compared to the case without the wrap. So your local stress concentration may not be very much, but about 20%. One has to be careful about understanding of this before one can go simply.
One final question before we can wait for lunch.
Sure.
So you spoke about intermittent coating, and related to that, it was for fire retardants. And what if in the protrusion process we use zinc powder, ATH, things like that, that already make it fire retardant? So is intermittent coating required there?
No. Well, I'm sorry, my fault. Okay. A filler is a fire retardant, calcium carbonate, for example. We also have other fire retardants, like you just said, the ATH. Any extraneous material is going to degrade the strength of the material. Keep that in mind. As I said before, filler will help not only in terms of fire retardancy, but shrinkage values and things like, and also the cost issues. Therefore, we must have a filler, no matter what. Then if you add ATH or whatever, you are going to get into further degradation in the material property, which is all right. But those additives are not bad, but really not quite as effective as the more recent intermediate coating or even the shields. That's the message I want to give you. Did that answer the question?
Also, the high quality resin, the cost also goes up.
Goes up.
Compared to that, this is cheaper.
Exactly. Yeah.
Okay, I think.
Yeah, he has a question.
One more question. Yeah.
You mentioned
You have to be louder.
so you mentioned like we design FRP structures based on flexible rigidity rather than stiffness.
No. Stiffness is the one that controls. You will see from my design example, every time you look at it, it is the stiffness. See, in any design, broadly speaking, we have two kinds of limit states. Broadly, I don't want to get into all the other detail. Strength limit state and the stiffness limit state. We have other limit states like extreme events or fracture fatigue limit. Keeping those aside, between the strength and stiffness, the design is controlled by stiffness limit state, which is the rigidity. EI is the rigidity, right? Okay, what's your question now?
So as you mentioned, like we design these FRP structures based on flexible rigidity. So are we going to end up providing larger FRP sections compared to steel?
Okay, I'm glad you're getting there. That is the issue we're dealing with. Why do you think I have had a foam core with FRP shell? I'm increasing my shell here and here with this distance, and I am getting higher AD square. So that doesn't mean I can increase it to 30 inches or 50 inches and it is like the golden goose, that guy cut his stomach like thing. So you will not have the top composite shell and the bottom. They have to act in unison for your AD square to work. So that is where all these different failure modes come. I will touch upon it when we get into the design. Okay, I still didn't answer your question.
My question is that compared to steel, in case of FRP structure, if we design based on flexible rigidity, so are we going to end up providing more larger section that will increase the cost also?
So the basically, I think the EI, if you want to make it same equivalent, you will end up providing more area. Is a question.
Okay. We do not look or evaluate any section based on cost per pound. We don't. You know how we look at it? We look at it, the cost, based on unit performance. Okay, what does that mean? It's the next, these are technical terms, right? Let's look at an FRP. Pound per, I know only American costs, I don't know the Indian costs. Pound per pound basis, steel is 50 cents a pound. FRP is $2 a pound, right? But when I'm using so many linear feet, when I translate it, FRP is only 1/4 the cost, the weight of steel. Therefore, I have an advantage from a weight point of view, a factor of 4. Wait. Likewise, I have an advantage from the strength point of view, a factor of 2. So I have a total advantage of 8. Yes? my cost of FRP per pound is 5 times higher, but from a functional point of view, from a performance point of view, I need only 1/8 the weight of that of steel to replace 1-to-1 from a performance, right? So that's what I mean.
That's it, man. Well, just to give an idea, here, we are dealing with a lot of manufacturers who produce GFRP rebar, right? As Professor said, typically the cost of rebar now, 70, 75 rupees per kilo, right? But FRP rebar equivalent in kilogram, it works out to be 150, 160 rupees if they really do a good job. So like only double the cost. We are much cheaper than what they have in the US because of the labor is cheaper and so many other factors. But again, as Professor said, if you look at the overall density, the weight point of view, FRP is in general 3 to 4 times lighter, right? So overall, I think even from the life cycle point of view, even in the first cost also from material point of view, now we'll get into more cheaper options.
Right. I may have a slide, I may not, I don't remember. The building they built in Saudi Arabia recently, they declared it was with FRP 20% cheaper than with. Do you have it? I got the slide from Nani.
Okay.
I keep calling Nani because this fellow is his advisor, and he was also past president of ACI.
Sir, if the weight is less, even if the weight is less, the diameter is going to increase, and our cross-section will
Well,
increase.
from serviceability point of view, you end up putting more area, but still overall, I will be using less cost price. That's it.
Even the cost of concrete is increasing, you can,
Concrete cost will not increase,
because
but we end up putting, for
whether
example,
if cross-section is going to increase due to the increase in diameter.
not really, because if you look at from flexural section point of view, right? The amount of steel that typically we add in a beam is 2% by volume, not more, 2-3 max. So even if I double it, still with the same cross-section, but I end up putting more area parts. I think that professor can add. So, but still you'll be able to do it. Cross-section dimension doesn't change. But even if you put more area, but from weight point of view, still we end up, using less material and less cost.
And I didn't say a word about, I only talked about the initial cost factor of 5 times higher per pound, but 8 times better performance. It's only from the initial cost. But I guarantee you, my FRP stuff survives 100 years.
100 years.
So I didn't even look at the life cycle cost point of view.
You have to see overall. Not just individualize, but see the overall cost. It matters.
All right.